Ever wondered how your device retrieves and manipulates data from a database? It all happens thanks to something called client-server architecture. At its core, client-server architecture is a distributed computing model. It's a way of organizing and dividing tasks or workloads between two elements, the clients and the servers. Now you might think, what does this have to do with databases? Well, in the realm of database systems, client-server architecture is pivotal. It dictates how database components and functionalities are distributed across client machines and server machines. So, what are these clients and servers? Clients can be thought of as end-user devices or applications that request and consume data from the server. This could be anything from your desktop computer, your smartphone, a web browser, or even specific client applications. These clients interact with the database server through user interfaces or application programming interfaces, also known as APIs. On the other side of the equation, we have servers. These are dedicated machines or instances that bear the responsibility of storing and managing the database. The software on these servers handles everything from data storage and retrieval to manipulation and security. And when it comes to examples of database servers, you've probably heard of a few: MySQL, Oracle Database, Microsoft SQL Server, and NoSQL databases like MongoDB and Cassandra, to name a few. The magic happens when clients and servers communicate. This typically occurs over a network using a standardized communication protocol. These protocols might be something like TCP/IP, HTTP, SOAP, REST, or ODBC. In this dance of data, the clients send requests to the server. These could be for data retrieval, insertion, updating, or deletion. The server then processes these requests, performs the required database operations, and sends back the results or confirmation to the clients. This architecture isn't just about functionality, though. It's also about concurrency, scalability, and security. It's designed to handle multiple client connections simultaneously, manage data consistency, and protect data integrity and confidentiality. So in essence, client-server architecture is the backbone of database communication. Without it, we wouldn't be able to retrieve or manipulate data as efficiently as we can. Now that we have a basic understanding of client-server architecture, let's delve into the first part of this duo, the client components. In the grand scheme of client-server architecture, clients are the end-user devices or applications that request and consume data from the server. They are the initiators, the ones who kickstart the data journey. They can be as varied as the devices we use every day: desktop computers, laptops, smartphones, tablets. Even web browsers and specific client applications fall under this category. The interaction between clients and the database server happens through a user interface or an application programming interface, commonly known as an API. This interface is like a bridge, connecting the client's requests to the server's vast pool of data. So how does this interaction work? Well, imagine you're using a web browser to search for a piece of information. You type in your query, hit enter, and voila! You're acting as a client, sending a request to a server somewhere in the world. The server receives your request, processes it, and sends back the information you were looking for. And all this happens in the blink of an eye. Of course, not all clients are created equal. Some clients are thick, meaning they carry out a lot of processing on the client side, reducing the load on the server. On the other hand, thin clients do minimal processing, relying heavily on the server. The choice between thick and thin clients depends on various factors like the complexity of tasks, network bandwidth, and the power of the client device. Moreover, clients can perform various types of operations on the data. They can request to retrieve data, add new data, modify existing data, or even remove data. These operations translate into select, insert, update, and delete queries in the database jargon. In summary, clients are a crucial component of the client-server architecture. They serve as the starting point for data requests and play a pivotal role in the overall functioning of a database system. Whether it's a desktop computer, a smartphone, or a web browser, clients are the initiators of data requests in a database system. With a clear understanding of clients, we now turn our attention to the other half of the equation, the server components. The server in the client-server architecture is the dedicated powerhouse responsible for storing and managing the database. It's the one that takes the requests from clients, processes them, and sends back the requested data or performs the requested operations. Think of servers as the librarians of the digital world. Just as a librarian retrieves books based on the reader's request, servers fetch data based on client demand. This is achieved through the magic of database server software, which is responsible for managing data storage, retrieval, manipulation, and security. But just as there are different types of librarians, from those in small community libraries to those in large university libraries, there are also different types of database servers. These range from relational database management systems, or RDBMS, like MySQL, Oracle Database, Microsoft SQL Server, and PostgreSQL, to NoSQL databases such as MongoDB, Cassandra, and Redis. Each of these has its own strengths and is chosen based on the specific needs of the system. Now, let's delve a little deeper into the responsibilities of these servers. The server's primary role is to manage the database. This means it's in charge of storing the data, ensuring it's organized in a way that makes sense and can be easily retrieved. But the server's job doesn't stop there. It also has to manage the security of the data, protecting it from unauthorized access, and ensuring that only those with the right permissions can access the information they need. The server also has a vital role in processing client requests. When a client sends a request, the server quickly springs into action, processing the request and returning the requested data, or performing the requested operation. This could be anything from retrieving a specific piece of data to updating an existing record, or even deleting data. And so, from MySQL to MongoDB, servers are the workhorses of a database system, processing client requests and ensuring data security. They might not always be in the limelight, but without them, the digital world as we know it would simply grind to a halt. Communication is key in any relationship, including between clients and servers. But how does this communication take place? Well, it's all thanks to a standardized communication protocol. This protocol, which can range from Transmission Control Protocol, Internet Protocol, TCP/IP, to Representational State Transfer, REST, among others, facilitates the interaction between clients and servers over a network. Now, let's break down how clients and servers actually interact. Clients, which can be anything from your laptop to your smartphone, send requests to the server. These requests can be for data retrieval, insertion, updating, or deletion. The server in turn processes these requests. It performs the necessary database operations, be it storing, retrieving, or manipulating data, and then it sends back the results, or a confirmation to the clients. You might be wondering how multiple clients can send requests to the server at the same time. Well, that's the beauty of client-server architecture. It's designed to handle multiple client connections simultaneously. So, whether you're using a database for your business or a social media app, rest assured that the server can handle all the requests it receives. But there's one more important aspect to consider: security. When clients send requests to the server, they need to authenticate themselves first. This ensures that only authorized users have access to sensitive data. The server enforces access control policies to restrict unauthorized access, thereby protecting data integrity and confidentiality. So in a nutshell, the communication protocol is the language that clients and servers use to talk to each other. It ensures that requests from clients are understood by the server, and responses from the server are understood by the clients. This process of sending requests and receiving responses is a continuous loop, ensuring that data is always accessible and up to date. Whether it's TCP/IP or REST, the communication protocol ensures smooth and standardized interaction between clients and servers. Concurrency, scalability, and security are three essential aspects of any database system. But how does client-server architecture support these? Well, let's start with concurrency. In a client-server architecture, multiple clients can access the database server simultaneously. To maintain data consistency and integrity, servers employ concurrency control mechanisms. This means when two clients attempt to modify the same data simultaneously, the server ensures that one operation is completed before the other begins. Now, onto scalability. As the number of clients or the volume of data increases, we need a way to accommodate this growth. This is where scalability comes into play. Client-server architecture allows for both horizontal and vertical scaling. Horizontal scaling involves adding more servers to the system, distributing the load and increasing capacity. Vertical scaling, on the other hand, involves upgrading the server's hardware, boosting its processing power to handle more tasks. Finally, let's discuss security. In a world where data breaches are increasingly common, security is paramount. Client-server architecture implements several measures to safeguard data. First, there's authentication. Clients must prove their identity to the server before they can access sensitive data. Once authenticated, the server uses access control policies to determine what data the client can access and what operations they can perform. Additionally, encryption is often used to protect data during transmission, ensuring that even if data is intercepted, it remains unreadable to unauthorized parties. To summarize, client-server architecture supports concurrency by managing multiple client connections and ensuring data consistency. It supports scalability by allowing for the addition of more servers or upgrading of existing ones. And it supports security through authentication, access control, and encryption. From handling multiple connections to ensuring data security, client-server architecture plays a pivotal role in the efficient and secure operation of database systems.